Hi everybody. We're going to just go through 5D, these stretches. So again, we want to look at how it affects the Y value and how it affects the X value. We've seen before things outside of the f of x notation, like this P, you're going to see is affecting the Y value. And these written inside this f of x notation, connected to the X, affects the Q values. We're talking about P being greater than 0, Q greater than 0. But we'll also look at that later with the flips, where P could be positive or negative when we're doing a flip. Anyway, we haven't worked through this investigation, but if we have a quick look at it, what we've done is got an x plus 2 function, our linear equation, and we're doing 3 times that function. That means 3 times x plus 2. So our original linear function is this blue line here, and with a y-intercept of at x y equal to 2. If we go 3 times that, then everything's going 3 times bigger. So every y value goes times 3. Our y-intercept now comes up at 6. And our x-intercept is 0, so it just stays the same because 0 times 3 is 0. Anything on the negative, if this is minus 1 on the blue, it becomes minus 3 on the green line. In the second example, so this was our green one, in our second example where we're doing this red one, where we've got half of f of x, so we're halving all the y values. So half of brackets x plus 2, and we could expand that. But basically, get your x, add 2 to it, so that does your x part of it. Now get your y value and halve it. So everything on the blue line is getting halved. So this is being halved. The y-intercept is going from 2 down to 1. So that's a little 1 for our y-intercept. The y value of our x-intercept is obviously 0. So 0 times a half is still 0. So we see our x-intercept doesn't change when we're doing a vertical stretch. Everything's being pulled up from the x-axis or down from the x-axis. And we have our multiplier, in this case was times a half, and in the first case was times 3. So we've got what we call a scale factor that we're multiplying by. So these first ones here are affecting y values. In the second example, where we've got an x squared function, we looked at in class, if we have f of 2x, then that becomes 2x all squared becomes 4x squared. And then in the second case where we've got f of 3x becomes 9x squared. So if we take our blue function as our y equals x squared, so this is our green one, 3x. So what we're seeing is it's much steeper. So in other words, in this case, if we get a point of 1 here, which would normally happen to give us a y value of that, because we've got 3x, the result we're getting is happening at a third. So to get that same y value, it's where x is a third. So if that's 1, here, this is at 1/3, it's not quite to scale. So we get the same y value, but a third. So we're sort of effectively squashing it in all the x values by a third. So our multiplier of the x values is a third. In this case here, when we have x over 4, it's the same as x squared over 16. So what would normally happen when x is 1, right? When I put 1 to that, we end up with 1/16. And that's the same result we would have got back here at a quarter. So down here. So our graph, if this is 0, there's no change. It's still our y and x-intercept. But our graph now is much wider. So this one is the opposite of the y stretches. So to come out of from here, we're doing a stretch in this case of 4. So when we have the constant, the value out the front of our f of x notation, it's affecting the y values. It's a y stretch. And the stretch was the same as the number in front, with a scale factor of p. Alright, whereas in this case, we're getting a stretch in the x direction, but if it's times 4, our x values are if it's a quarter, so in this case, the red one here, our q value is a quarter, but we find that the graph itself has been stretched outwards times 4. So it's the same as the scale factor of 1 over q. So it's the reciprocal of whatever number was in front of the x. So if the q is a quarter, then 1 over a quarter is 4. So that's why the whole graph is stretched outwards by 4. This is summarised in your textbook. So for p, with p being positive, p is greater than 1, it moves all the points further away from the y-axis, and the x-axis at least, it's a vertical stretch. If p is between 0 and 1, it moves it closer. So scale factor, so get the y values and multiply them by p. In the QX one, if we've got a positive Q, so we're not talking about doing any flips, we're getting a horizontal stretch, and our scale factor here is Q1 over Q. If Q is greater than 1, it moves all the points closer to the y-axis, so it's the opposite of what happened with the first case. If we get Q between 0 and 1, it moves them further away from the y-axis. So it's affecting our x values. So if I have f of 3x, my scale factor is a third, it's 1 over 3. If I have x over 5, in this case q equals 1/5, so our scale factor is 1 over 1/5, which is 5. So I know you're good at fractions. Alright. So this again is just going through a couple of questions here. I just wanted to look at the log function in particular. When we're doing this one here, in our log function, because we haven't put one of those on the recording. So our initial function for a log looks like that. If I go 2ln of x, it means all our y values have been multiplied by 2. So this is going to go double the height, that will go to there, this will come up to here, that will come up there. And if I wrap that up, that should match. Alright, almost matching it. Alright. Note, this point stays the same, our x-intercept stays the same because the y value there is 0, and it just y times 0 times whatever the scale factor stays the same, and this is getting stretched further away, so everything's going further away from the x-axis. So this comes down further away from your x-axis with that stretch. If I did y in the third, y and natural log of x over 3, our scale factor here is 3. Right? So that means our y's will be multiplied by 3, so that will do a vertical stretch away from as well. Or at least all our x values will be stretched out by 3. So making that flatter. I might just rub that out so we can grab that and see what this one does. I'll make that one. So this one here is flatter out, it gets stretched, so all our x values are 3 times out further. So this was at 1, the x-intercept now is at 3, 1 times 3. So our 1, 0 goes to 0, oops, 3, 0. There's a couple of other examples I want to look at. One, sorry back here, I just wanted to include, I didn't go through this scale factors. Note, when you're multiplying a stretch in the y direction, you're getting no change in the x-intercepts we talked about. What I didn't talk about was if you've got a vertical asymptote, obviously if you do a vertical stretch, that doesn't change. In the horizontal, if there's going to be no change in your y-intercepts, because you're stretching out horizontally from the y-axis, so they will stay the same. If you've got a horizontal asymptote, that will also stay the same in a horizontal stretch. So that was one point I just forgot to mention earlier. And one other one here, I just wanted to quickly run through. If we've got this function here, with that sort of notation, 3f of x over 2. 3 tells us we have a vertical stretch of 3. Times 3. And a horizontal stretch. Times 2. So our q value here is 1 over 2, and we take the reciprocal. 1 over q equals 2. Doesn't matter what order I do this in. Doesn't matter whether I stretch it vertically and then horizontally, or vice versa. Because it is affecting the x and the y and they're different, the order doesn't matter. It's only when you get 2 things happening to the x's the order matters, or 2 things happening to the y, then the order matters. So in this case, no, it doesn't matter. So if I did say the vertical stretch first, let's do that. So that stays the same. 1, 2, 3, 4. So this is going to come up to 12. That's a 12. 1, 2, 3. Comes up to 9. 2, 3, 1, 2, 3. So this is at 9. Not fitting on the board, but that's at 9. So that means that's our vertical stretch. Okay. And then our horizontal stretch times 2. So all our x values become double. So this one stays the same because it's on the y-axis. This was at 1, 2, minus 3. 1, 2. So this now becomes minus 3 out of that. So it's minus 6. And 6. That stays the same. So that will be 12 and 0. This is at 1, so it now comes out to 3. So this point comes out here, and this point at 1, 2, 3 comes out to 9. So our graph looks like this, that. So this is now at 9, 9, and this one here is now here, so we're at 3, 9, 12, 0, minus 6, 0. All right, so you can try doing it the other way and it will work the same. All right, we'll leave it there. Hopefully that will help you as you go through those questions. Thanks for listening. Bye for now.